Welcome to the School of Batman, a podcast where we ask academics to help Batman fight crime using their research. I'm your host, Chris George, amateur scientist and professional Batman enthusiast. In today's episode, we'll be discussing the case of the Fists of Bane. We're pleased to be joined by Chris Wynder, who has a PhD in developmental neurobiology from Rockefeller University. So Chris, we like to start the podcast with some background on yourself, your journey, what inspired some of your choices, and a little bit about your research and how you got to be where you were.
So as you mentioned, I have my PhD from Rockefeller University, and then after that I went on to, my interest has always been in the brain, how it functions, and sort of how you made it, right? So that was always the most interesting question to me, is how you made it. So I went on to do a postdoc in stem cells because, again, how you make it, how you remake it in case of injury or in case of disease were really interesting questions. And then after that, I took some time and did another postdoc in a drug discovery lab that focused on epigenetics and how do we modulate this thing that we call epigenetics, which in some ways is really just how do we decide what books the cell's going to read from to decide what it's going to do with its life. Much like many of us, we read a book to get where we're going to get. Then after that, I was an assistant professor at a university looking at drug discovery and traumatic brain injury and subconcussive, and how do we get ahead of these problems when we know that there's going to be an issue to the brain. Because we can't just replace cells and have the brain function properly, we really need to focus on how do we repair what's already there. We have to maintain what's there as long as we can to make sure that the system functions.
So developmental neurobiology, is that about kids growing into adults, or is that about how the brain changes as an adult?
Yeah, typically when we talk about developmental neurobiology, we're even before that, right? We're at the point of how did we get from a ball of cells to a ball of cells that functions as a full brain, can manage all the body and integrate itself into your whole body. So for example, we know that the way the brain builds itself has a weird structure. It starts off as a ball of cells that don't know that they're the brain yet, and starts to put cells in place so that it can develop itself into a brain, but it doesn't let the cells know that they're a brain. So the developmental neurobiology is really about that idea of how did we go from regular cells to neural cells, and then it becomes into more of that regular neurobiology, which is when we're talking about post-birth. So again, it's pre-birth more so than post-birth.
So how does that even begin to start? So I am imagining a fetus, I'm imagining a kind of ball of cells at the start, but it's the in-between, which is beyond me. So could you talk a little bit about that?
Yeah. So and that's the really cool part to me is, the ball of cells is interesting because there's all kinds of things that can happen. At some point, the ball of cells becomes slightly differentiated, becomes more of a tube. And once you have a tube, you have poles. You have a left side and a right side. You have a top and a bottom. You have all these areas of discrimination. So once the ball of cells turns into a tube, you now have what will turn out to be the top end. And once you know that you're at the top end, you also know where the brain's going to be. So those are all the contexts, the things that have to be known before you can actually figure out what the brain is, where the brain is, and how to build it. So once you get that tube, you get to that point where you're not quite a fetus, but you're not a ball of cells. From that, there's a set of signals that say, okay, we're the top end, everybody else be something else. From that, we then start to differentiate off, and that's when we start talking about different tissues and organs. That's when we start to get to what is then known as the neural tube stage, where we then break off a set of cells from the top and what will be known as the back, and these become the neural tube. Once we have that, those cells are predestined to become the brain and the spinal cord and some of the other neural cell types. Once we get to that definition, we start to expand the mass at one end of this tube, and that becomes the brain. Now we're just talking about layers of differences, right? Because we have additional types of neurons that we're going to have to make once we figure out that we're a brain. We have to figure out what area of the brain we are, what kind of neural cell we are, who do we talk to, when do we talk, how do we control X, right? So it's this kind of step-by-step building, which was really attractive to me as a scientist, and is still really attractive to me as a scientist, of how do we decide the process of making a brain? Because you could think how you just want to make a ball of cells and have them build a brain out of themselves, and that might work too, but we don't actually do it that way. We do it the exact opposite.
And you said the word predestined there, which was a very kind of interesting word to say. What does that mean, predestined? How can a cell be predestined?
The analogy I like to use is, and this is where kind of epigenetics and transcriptional regulation come into play, is I like to think of it as a book of life. Every human has a very similar to the point of, I believe the last number I saw is, I think, were approximately 99.x% the same at the level of the genome. So the base pairs, the ATGCs, were about 99% similar, but we all look very different. And the way that you get to that difference is which parts of it you decide to express, and more importantly, when we talk about that predestined part, how much of each. So we only have so many genes that we have, and we have to figure out how do we build different things out of the limited number of things we have. And the way you can control that is amount of X triggers a different reaction, and the type of X triggers a different reaction.
Fantastic, thank you. So I think it's probably time we move on to your story. So before we get to your story, we ask our guests to choose a Batman actor to represent their Batman in their story. So do you have a choice for yours?
Yeah, I think my favorite representation in film of Batman is Christian Bale. I like where that came from, and it seems to come from the Frank Miller version of Batman, which is my favorite of all the different readings or writings of Batman.
Great choice. An exhausted Batman turns in for the night after another evening of capturing escapees from the recent Blackgate prison incident, where most of the city's dangerous were let loose to the streets of Gotham by Bane. Watching in the shadows, biding his time, the South American destroyer strikes at the very heart of Batman, crashing through the windows of Wayne Manor and delivering a brutal attack. Discovered by Alfred as soon as Bane leaves the building, the flurry of blows to the head of Master Bruce are hugely concerning. Alfred calls upon an old friend. So in this story, you are the old friend. So Batman has received some pretty severe trauma to the head, and one can assume the brain as well. So how could your research help Batman in this time of need? Yeah,
so it's an interesting aspect of one of the studies that we did was we were looking at how do you actually reverse some of the damage. So we know when the brain gets damaged, you have an initial reaction which the brain thinks is going to help but actually doesn't help, and it's the overcreation of a brain cell type called glia. So we do know, and they're essentially the scar in this case. So they're sort of the scar tissue of the brain, similar to when you get a scab. What we do know now is that if the reaction to the brain injury is too extreme and we create too much glia, we actually do more damage than it protects the brain from. So one area that we were studying was looking at the kind of drugs, the kind of external signals we can give to the brain. So again, not creating more damage by going in and drilling into the brain, but the kind of pill or tablet. In this case, I would want to give him, for lack of a better term, an elixir or a tablet early on, right after we got there, so we can reduce the amount of inflammation specific to the brain. So these cells aren't like normal scab where you can put a cream on it and it reduces the cream. It's not like the Q10 formulas you can get. It would be a very specific pill that wouldn't have any effects on the rest of the body, but when it crossed the blood-brain barrier, it would be able to diminish the response of those cells, not stop it, but diminish it so that you're getting the protective part of that expansion without getting the bad parts of it, which cause too much swelling in the brain, which then causes more long-term issues. So that would be our initial focus, and then it would be thinking about a treatment plan to make sure that we are regenerating the neurons in the brain rather than having to allow those neurons to die.
Right, I'm going to take you right back to the start of what you said there. So you mentioned something called glia cells, and you said they're kind of like something which promotes scarring. Is that right? Did I understand you?
Yeah, that's one aspect of what they do. They're a complicated cell, so it's sort of like a combination of your immune system and your skeletal system and your pancreas, for lack of a better organ, all wrapped into one cell type. So it's a really weird cell type. We're just kind of wrapping our heads around it research-wise, what it actually does in the brain.
It doesn't seem logical that there would be such an amount that could cause problems to Batman himself. So is that a case of brain development has superseded the response to getting this overabundance of glia cells, or is there other things that maybe we don't understand yet? It seems kind of counterintuitive.
It's extraordinarily counterintuitive, and we're just kind of wrapping our heads around why it might happen, right? So one of the things that we know happens is when you damage the brain, the area of damage sends out a signal that it's been damaged, and the damaged area needs more energy. So neurons can't synthesize their own energy sources; they get it from the glia. So again, that pancreas analogy. They also need to clean up whatever damage has been done. And again, neural cells can't do that, and that's the glia. So you get this very overexuberant response where the way the body in the rest of the body responds is you make too much and then you use what you use and you kind of reabsorb what you don't. In the brain, where you have a limit in how much extra you can put in there, this overexuberance of making too much so that you know you have enough causes real issues. And that's where we get into these problems when we're talking about glia, is this problem of the normal developmental response is to make too much and get rid of, in a programmed way, the stuff you don't need. In the brain, in an adult, that becomes an issue.
All right. Okay. So you've got Bane pounding on the sides of your skulls. What type of, this may be beyond your purview, but what type of damage could be expected in Batman's head there? Like what type of things untreated? Where could this go? Where could this lead?
Yeah, so the most obvious one, and it's a big issue over here for sports fans, is really CTE. So which is the long-term result of chronic brain injuries. The short term is what we call TBI, so traumatic brain injuries. Your skull does a really good job of protecting you from external damage. What it doesn't do a good job of protecting you from is shaking. So a punch to the head is going to cause a wave of energy to go from your skull into the fluid that surrounds your brain into your brain. If it's hard enough, it's going to cause your brain to go from its normal position and squish against the other side of the skull.
I think a punch from Bane, we could safely assume that it's going to be hard enough.
Yeah.
So I think that's reasonable. So let's go with the assumption that it's hard enough. What would happen next?
Yeah. So on the side of the brain that hit into the skull, you would get, for lack of a better term, a bruise, where you have damage to the cells based on getting mechanically squished, right? On that side of the brain, you're going to have bruising kind of symptoms, and this is where we get that overexuberance of glia. On the side that you got hit, assuming, for some of those, and this is in many ways outside my purview, but what you would see is, potentially small cracks in the brain leading to fragments getting embedded into the skull, and you could have a different kind of injury on that side of the brain. So you have that swelling kind of injury and that kind of fragment into the brain kind of injury.
Right, so this initial treatment is going to reduce the flow of glia to a level where he's going to be able to recover from those initial injuries better. And then you said there was a secondary aspect to it, which is about untreated. You said some of the cells have a potential to die. Could you talk a little bit about that?
Yeah, so your body has a really cool mechanism for cleaning up and getting ready to rebuild a tissue. Um, and that's called apoptosis. And really what that is programmed cell death. And what that means is we take the building down. In this case, we take the cell down in parts and package it up, and it all gets recycled, and it's all a very neat and orderly process. You can have another kind where you literally do too much damage to the cell and it explodes or just melts away. This melting away kind causes other issues, and we call this necrosis, or an unprogrammed cell death. And this causes the cells around it to be poisoned, essentially. What we want to do short term is make sure that we reduce the glia so we can make sure that the cells that die in a programmed way. Again, we recycle them. Once we've gotten to that point where we're ready to recycle, we figured out which cells are damaged, we've gotten rid of those. We now then have to have a program to replace them. In the brain, that doesn't happen all that well, and that's one of the issues that we find out that we're now starting to understand. It's just how bad the brain is at fixing itself.
So that response, if something is quite extreme, those cells that you say might get poisoned, they might be perfectly healthy cells. Is that right?
Yeah.
Right. So this going untreated, this could cause a large number of his healthy brain cells to be poisoned and to die at the same time, which is obviously going to cause a lot of problems. So how could you go into a little bit maybe about some of the technicalities of how you're able to reduce that kind of, what did you call it, a mass explosion or something like that? How do you go about targeting that?
Yeah, so one of the ways that is typically done is, and that's one of the reasons we get that over exuberance of glia, is that the brain is very well manicured, as it were. The glia are always there trying to test the neurons, make sure that they haven't been poisoned. But we want to make sure that we get the right kind of glia. So there's, like any time we're talking about cells, there's always subdivision of labor. So the other part of what we can do from a treatment perspective is try and make sure that we're pushing the glia to be more of the manicure side and rather than the inflammation side. Make sure that any cells that have been poisoned, instead of just tearing them down, essentially they're acting like doctor cells. They're giving the cells energy. They're kind of sopping up all the poisons around those healthy cells, so that now there's an environment for that neuron that is healthy. It's that environmental cleanup aspect of it.
Right. So we've got this combination, and is there anything that we can do? So we've managed to stem the initial scarring from this beatdown. We've managed to stem some of the collateral damage of trying to get rid of some of these cells which are definitely beyond repair. Is there anything that we can do to promote regeneration in those cells that have been lost?
Yeah, so this is early days in this research, so a lot of this aspect of it is very speculative. But at the same time, we think we have an idea of what you would have to do from a treatment perspective. So we know that there's a reservoir of cells in your brain, and these are called stem cells. So these are cells that, while they know they're part of the brain, haven't decided whether they're going to be the glia or they're going to be a brain cell. So what we can do is, as we start this cleanup, and once we've gotten past that initial inflammation, we're however long after, say a week after, we know that there's no further initial inflammation going on or damage, and we're now in the process of rebuild. We want to make sure that we've instead of having that overexuberance and continuing to make more glia, we've now changed this over to a process where we're telling these extra cells, you know what, we've got enough glia, we want to make more neurons, and we need you to ramp up production. The treatment would be a combination of telling the reservoir to ramp up production, and as they're ramping up production, to remind them, don't be glia, be neurons. So it'd be a combination treatment within the brain of informing the cells that we need more of them, and making sure that we're making more of the right kind.
Right, you mentioned the word there, reservoir, which was interesting. So as an adult crime-fighting Batman, do I have a reservoir of stem cells available to me to call upon?
You do, actually, and and this is kind of, this was groundbreaking when I was doing my postdoc. This was thought not to be true. And while it's not controversial, we're not clear how big a reservoir adults have, and we're not clear that it is a every cell in the brain reservoir. And so this is where we're at as far as the research now in kind of neurobiology and neurostem cell biology.
So that's all for now. It looks like Batman is back on the road to recovery. And thanks for listening. Thanks to Chris Wynder for joining us.
Thanks for having me, Chris.
And you can follow Chris at CW_InfoGardener on Twitter. If you'd like to discuss your research on a future episode, email us at info@figshare.com.